In order to solve systems of linear equations, we're going to develop an algorithm called Gaussian elimination. This algorithm will depend on the three basic operations that we define in this video. The first one is called scaling. We know that if we have an equation, we can always multiply both sides of the equation by any non-zero number. So if, for example, we want to scale the equation negative x plus y equals 1 by 2, then we get the equation negative 2x plus 2y equals 2. We know that this does not change the solutions to our linear equation. So we can take an m by n linear system, scale any equation that we like, and get an equivalent system. The next operation that we can perform on a system is called interchange. It's called interchange because we may interchange any two equations in the system, which just means reversing the order in which they appear. So as an example, I started with the system negative x plus y equals 1 and negative 2x plus y equals minus 1. Then I flip the order in which these two equations appear to get the system negative 2x plus y equals negative 1 and negative x plus y equals 1. And these two systems have the same solutions, so they're equivalent. Our third operation is called replacement. In replacement, we scale one equation, then we add it to another equation. This also preserves our solution set, so we get an equivalent system. So in this example, let's consider the system negative x plus y equals 1, negative 2x plus y equals negative 1. We can, for example, scale the top equation by minus 2, then add it to the second equation. We're calling this operation replacement because we're replacing the second equation here. We arrange it in this way so we can add down the columns. So this gives us our new equivalent system, negative x plus y equals 1, and our replaced second equation is negative y equals negative 3. At this point, we can see how to solve this equation. The first thing I'm going to do is I'm going to replace equation 1 with equation 1 plus equation 2. Now finally, I'm going to scale both of my equations by negative 1. Now we have what's called a decoupled system. So the system that we started with, which was negative x plus y equals 1 and negative 2x plus y equals minus 1, has exactly one solution, and that solution is the point in R2, 2, 3. Geometrically, this should make sense. The set of solutions to each of these equations carves out a line in R2. So if we're looking for simultaneous solutions, we're looking for a point that lies on the line negative x plus y equals 1 and the line negative 2x plus y equals minus 1. So to graph negative x plus y equals 1, we just plot the 2 points, negative 1, 0 and 0, 1, and then we draw a line through these 2 points. To plot the other line, negative 2x plus y equals minus 1, we plot the point 0, minus 1, the point 1/2, 0, and then we draw a line through these 2 points. The point of intersection between these two is, in fact, the point 2, 3. So to give you some sort of idea about how things can get quite messy, let's turn back to our 4x4 system. So my goal is to end up getting a 4x4 decoupled system. A equals something, B equals something, C equals something, and D equals something. To do that, I'm going to use only the 3 operations that we've defined. So my first goal is to use one of the equations to get rid of the rest of the A's. I'm going to use the first equation. To get rid of the A, in the second equation, I can add the first equation to the second equation. That's a replacement. Next, I'm going to use the first equation to remove the a from the third equation. I'm going to multiply the first equation by -1 and add it to the third equation, which of course is the same thing as subtracting the first equation from the third equation. My next operation is going to be to add the first equation to the fourth equation. Now that I've gotten rid of the a's, my next task is to get rid of the b's. If I use my first equation in a replacement operation, then I'm going to reintroduce a's no matter what I do. So for the rest of this, I will not use that first equation at all. To clear the b's, I'm going to use the second equation. So I'm going to take the second equation and I'm going to subtract that from the fourth equation. For my next operation, I want to get rid of the c's, and I can also get rid of the d's. So the first thing I'm going to do is scale the third equation by -1/2, and I'm also going to scale the fourth equation by -1/2. The next thing I can do is I can work my way back up. I'm going to, starting from the bottom, I'm going to use this d to remove any d's above it. There's only one, so I'm going to subtract the fourth equation from the second. Now that I've removed all the d's, I'm going to use the third equation to remove all the c's. I'm going to subtract the third equation from the second and also from the first. Next, I'm going to scale the second equation by 1/2. Finally, all I have to do is subtract the second equation from the first, and I'm left with the decoupled system, which tells us that our system of 4 equations in 4 unknowns only has one solution, and that solution is the quadruple -1, 1, 0, 4. So as you can see, performing operations directly on systems of equations can be really nasty. So before we describe the Gaussian elimination algorithm in its full generality, we're going to develop some shorthand notation, and that's going to be called an augmented matrix.